Oh, good, it's working. Oh, good, it's working. Oops. Okay, we have about a minute to spare or so. Well, it's pretty close to 9 o'clock. Today and tomorrow we'll be in section 7.4 on integrals of rational functions by the partial fractions method. Then on Friday, section 7.5 is strategy for integration. So it'll be a review of the methods that were discussed previously. Okay, so let's go ahead and start section 7.4. Hey, I've assigned for practice from the textbook 10 problems from section 7.4. You can do more if you like. At least read through the section and work through the examples. Recall that a rational function has the form f of x equals p of x divided by q of x, where p of x and q of x are polynomial functions. If the degree of the function in the numerator, that is, if the degree of p of x is less than the degree of q of x, then we say that the rational function is proper. That is, f of x equals p of x over q of x is called a proper rational function. And it can be expressed as a sum of simpler fractions. In the same way that an ordinary fraction, such as 4/7, is referred to as a proper fraction, proper rational functions behave in a similar way. Okay, so here's an example. In the previous sentence, it said that proper rational functions sometimes can be expressed as a sum of simpler fractions. So for this function, this rational function, f of x equals 3x squared plus x plus 5 divided by x to the third plus 2x squared plus x plus 2. Let's verify that this rational function is equal to the sum of these two simpler rational functions. So the way that we can do that is we can just do what we do in regular ordinary arithmetic. We need a common denominator. So for the fraction 1 over x squared plus 1, I'm going to multiply that fraction by 1 in the form x plus 2 over x plus 2. I'm choosing x plus 2 over x plus 2 because the other denominator is x plus 2. Then we'll multiply the fraction on the right, 3 over x plus 2. We'll multiply that by 1 in the form x squared plus 1 divided by x squared plus 1. Now we have a common denominator. The common denominator in factored form is x plus 2 times x squared plus 1. And then we do the arithmetic in the numerator. So we have 1 times the binomial x plus 2, which is x plus 2. Then we're adding 3 times the quantity x squared plus 1. So that's plus 3x squared plus 3. And we'll simplify it a little further to write the numerator in standard form. We write 3x squared plus x plus 5. And we'll go ahead and multiply the two factors in the denominator. So x times x squared is x to the third, and then plus 2x squared plus x times 1, or just plus x, and then plus 2 times 1, or plus 2. Okay, so that means we can evaluate this indefinite integral of that rational function by first writing it as an indefinite integral of a sum of simpler fractions. Okay, so we're just going to, instead of writing this entire rational function, we're going to write it as this sum, the indefinite integral of 1 over x squared plus 1 plus 3 over x plus 2 dx. And we know how to evaluate this indefinite integral. We get an opportunity to practice a trig substitution for one of them. So let's write this as a sum of 2 separate indefinite integrals. The indefinite integral of 1 over x squared plus 1 dx plus the indefinite integral of 3 over x plus 2 dx. Okay, the one on the left, let's work on that for a minute. The indefinite integral of 1 over x squared plus 1. So in the denominator, x squared plus 1, if we use a trig substitution, x equals tangent of theta, then dx is secant of theta squared d theta. And when we replace x with tangent of theta, we're going to get, I'll write dx, what dx is equal to in the numerator. So the numerator, we can write it as secant of theta squared d theta. And in the denominator, replace x with tangent of theta, we get tangent of theta squared plus 1. Tangent of theta squared plus 1 is secant of theta squared. So in the numerator, we have secant of theta squared d theta. In the denominator, we have secant of theta squared. So secant of theta squared divided by itself is 1. So we just get the indefinite integral of d theta, which is theta plus the constant. And we know what theta is because our assignment for the substitution is x equals tangent of theta. So theta is just the inverse tangent of x. Okay, so that is the answer to the indefinite integral on the left. Inverse tangent of x. Plus a constant. Hey, what about the other indefinite integral, this one? We've seen this kind of thing before a few times. So if we just look at that by itself, we can write this as 3 times 1 over x plus 2 dx. So this is just going to be 3 times the natural log of the absolute value of x plus 2. Okay, so up here I'll write the final result. We have inverse tangent of x, and then plus 3 times the natural log of the absolute value of x plus 2 plus a constant. That's the answer. So perhaps you'll see that using this partial fractions method makes the process easier when you look at this indefinite integral of this original rational function. It looks pretty complicated. Okay, let's move on to the next page. If we start out with a rational function that's improper, that means the degree of p of x is greater than or equal to the degree of q of x. Then what we want to do first, we want to divide p of x by q of x. So you'll remember from algebra, if you use long division, if you divide p of x by q of x, when the degree of p of x is greater than the degree of q of x, greater than or equal to, you'll get a quotient. Here we're calling the quotient capital S of x, plus the remainder r of x divided by q of x. And the quotient capital S of x, well, I've already mentioned, it's a polynomial. R of x, the remainder, is also a polynomial. And the degree of the remainder will be less than the degree of q of x. Okay, so in this next example, we're going to verify that this improper rational function, x to the third plus 8x squared plus 13x plus 7 divided by x plus 1, we're going to verify that it's equal to the polynomial x squared plus 7x plus 6 plus this simple rational function 1 over x plus 1. Okay, the way that you're going to probably have to do it, depending upon what you're dividing by, since we're just dividing by x plus 1, we could use synthetic division, but if the denominator is a higher degree polynomial, then long division is the way to go. So let's go ahead and divide the numerator by the denominator using long division, polynomial long division. We're going to divide x plus 1 into the numerator. x to the third plus 8x squared plus 13x plus 7 is the dividend. X will go into x to the third, x to the second times. Equivalently, we can find this first term in the quotient if you divide x to the third by x. Then we multiply x squared times each of the terms in the divisor. X to the second times x is x to the third. And then x to the second times 1 is positive x squared. In general, you have to pay attention to the terms and where you put them. They should go in the same column where the terms are like terms. Then we subtract. X to the third minus x to the third is 0. 8x to the second minus x to the second is 7x to the second. And then we start the cycle over again. X will go into 7x to the second plus 7x times. Then multiply 7x times the divisor. 7x times x is 7x to the second. And then plus 7x times 1. Then we subtract again. 7x squared minus 7x squared is 0. 13x minus 7x is 6x. And there's just one more cycle in the division. X goes into 6x 6 times. Multiply 6 times the divisor. 6 times x is 6x. Plus 6 times 1 plus 6. And then subtract. 6x minus 6x is 0. 7 minus 6 is 1. Okay, so in this example, capital S of x, that's the quotient, x squared plus 7x plus 6. The remainder is a degree 0 polynomial, but it's still a polynomial. The remainder is 1. And then if you remember, well, it's further up on the page, but p of x divided by q of x has the form s of x plus r of x divided by q of x. So you can see that everything worked out. This is our s of x, x squared plus 7x plus 6, plus the remainder 1 over the divisor q of x. Okay, so it all checks out. And we can evaluate this indefinite integral now by first writing it as the indefinite integral of the quotient from our division, x squared plus 7x plus 6, plus the remainder 1 over the divisor x plus 1 dx. And this is a very simple indefinite integral to evaluate. It looks a whole lot easier than what we started with. So the answer is x to the third over 3 plus 7x to the second over 2 plus 6x. And then the indefinite integral of 1 over x plus 1 is the natural log of the absolute value of x plus 1, and then plus a constant. Okay, the next page. So that's the introduction, just to show you the usefulness of the partial fractions method. Okay, integration of rational functions by partial fractions. Okay, and here's a statement to keep in mind. Any proper rational function can be integrated by first rewriting, if necessary, the rational function as a sum of simpler fractions called partial fractions, whose antiderivatives we already know how to find. Sometimes you'll have a rational function that is already as simple as it can be, but we'll know how to integrate it. If it's any more complicated than that, then we can write it as a sum of simpler fractions. Okay, we're going to follow the textbook. Basically, the textbook identifies 4 cases. So 4 cases will be described. And in each of the cases, we're going to assume that the rational function is already a proper rational function. If it's not a proper rational function, then we just divide the numerator by the denominator and then deal with the R of X over Q of X separately. Case 1, the denominator Q of X is a product of distinct linear factors, meaning that each of the linear factors is represented exactly once in the factorization of the denominator. A linear factor in the variable x can be written in the form ax plus b, where a and b are real numbers and a is not equal to 0. Okay, so in this case, if q of x, which is the denominator of the rational function, consists only of distinct linear factors, then it will look something like this. So a sub 1 times x plus b sub 1 times a sub 2x plus b sub 2, and so on. Each one of those linear factors is different from each of the others. No factor is repeated. Okay, well, that means that there exist constants, a sub 1, a sub 2, up through a sub k. So just note that in this factorization, there are k factors, k distinct linear factors. So there are k real numbers or k constants, such that p of x over q of x is a sub 1 over a sub 1x plus b sub 1 plus a sub 2 over a sub 2x plus b sub 2, and so on, until we get to the last one, a sub k over a sub kx plus b sub k. Okay, so here are k partial fractions. It's possible for the constant, some of the constants to be 0. So it might turn out that we don't actually get a full number k of partial fractions, but we have to allow for the possibility. Okay, so let's try that method on this. Evaluate this indefinite integral of the rational function. It's a proper rational function. The degree of the numerator is 2 and the degree of the denominator is 3. Well, using some techniques from algebra, we could determine what the factorization of the denominator is. Yeah, but we won't go into all that detail. I'll just rewrite the numerator 6x squared plus 22x plus 18. And the factorization of the denominator turns out to be x plus 1 times x plus 2 times x plus 3. Okay, so the denominator q of x consists of 3 distinct linear factors. So the partial fraction decomposition theorem says that there exist constants, 3 constants. I'm just going to use capitals A, B, and C for the constants instead of a sub 1, a sub 2, a sub 3. So I'm going to write it as a over x plus 1 plus b over x plus 2 plus c over x plus 3. So all we have to do is find the constants a, b, and c, and then we can evaluate the indefinite integral of 3 simpler fractions, which we already know ahead of time what the answer is going to look like, right? Just for example, the natural log of a over x plus 1 is a times the natural, did I say that right? The indefinite integral of a over x plus 1 is a times the natural log of x plus 1, and so on. So as soon as we find the values a, b, and c, we'll almost have it all done. There are a couple of techniques for finding a, b, and c. This one's going to be nice for one of the methods. So what we do is we multiply every term on both sides by the least common denominator, or the least common multiple of the denominators. So I'll note up here that the least common denominator is just the product of x plus 1, x plus 2, and x plus 3. Okay, that's the least common multiple of the denominators. When we multiply every term on both sides by that, on the left-hand side, we're just going to get 6x squared plus 22x plus 18. When we multiply the least common denominator by a over x plus 1, the x plus 1 factors cancel, and we'll just have a times x plus 2 times x plus 3. When we multiply the least common denominator by b over x plus 2, the x plus 2 factors cancel, and we're left with b times x plus 1 times x plus 3. And then for the last term, multiply c over x plus 3 by the least common denominator, the x plus 3 factors cancel, and we get plus c times x plus 1 times x plus 2. Okay, I think we can see everything. Okay, this method is kind of nice in a case like this. If we pick an x value that makes one of those factors 0, then we'll eliminate a bunch of the terms all at once, and it will enable us to solve for one of those values, a, b, and c. Okay, so to start with, one of the factors is x plus 2. The x value that makes x plus 2 0 is x equals -2. So I'm going to pick x to be -2. And then on both sides of the equation, I'm going to replace x with -2. So on the right-hand side, we have 6 times the number -2 squared is 6 times 4, plus 22 times -2 is minus 44, plus 18. We'll simplify this a little bit in a minute. But we don't have to write down everything. When we replace this x with -2, we get a factor of 0. So a times 0 times this factor is just 0. So we can ignore this because we get 0. The same is true for the factor on the right, since we have a factor of x plus 2. When x is -2, this is all 0. So we only have to pay attention to where the x plus 2 factor is absent. So this is equal to b times, and remember we are replacing x with -2. -2 plus 1 is -1. And in the other factor, -2 plus 3 is 1. So a little bit more arithmetic. We have 24 minus 44 is -20. -20 plus 18 is -2. -2 equals -b. So that means our value b is +2. So now we know that b is +2. Okay, let's go through the same process. This time, let's pick x to be -1. Then replace every x on both sides of the equation by -1. So 6 times -1 squared is 6. And then minus 22 plus 18. I'll just simplify a little bit. Minus 22 plus 18 is 6 minus 4. So the left-hand side is 2. Okay, then we look for the factors or the expressions that have the factor x plus 1. So when we replace this x with -1, this contributes 0. And the same on the other, on the end, we get 0. And so we have a times, and then -1 plus 2 is +1. -1 plus 3 is 2. So we get 2 equals 2a, which means the value of a is 1. Okay, just one more. Now we need to know what c is. Okay, the other factor, x plus 3, is 0 when x is -3. So replace every x with -3. Okay, so 6 times -3 squared is 6 times 9, or 54. And then 22 times -3 is -66. So we get 54 minus 66 plus 18. Okay, then on the right-hand side, when x is -3, this term becomes 0, the second term becomes 0. And now we're just have this term on the right. So c times, when x is -3, -3 plus 1 is -2. -3 plus 2 is -1. And now we just do a little bit of arithmetic. 54 minus 66 plus 16 is, that's +6. And we get c times -2 times -1 is 2c. So we get c equals 3. All right, so we can finish this. A is 1, so we get one of our partial fractions is 1 over x plus 1. B is 2, so we get 2 over x plus 2. C is 3, we get plus 3 over x plus 3. Okay, so the indefinite integral, I won't rewrite the original, I'll just write the indefinite integral of the partial fractions. So we know how to evaluate each one of those. Okay, so one of those is the natural log, the indefinite integral of 1 over x plus 1 is the natural log of x plus 1. And the indefinite integral of 2 over x plus 2 is 2 times the natural log of x plus 2. And the indefinite integral of 3 over x plus 1 is 3 times the natural log of x plus 3. And then plus constant. It seems that a lot of people don't really like partial fractions because of the tediousness involved in finding the partial fractions. But it's still a good method. Hey, let's look at case 2 for a while. Hey, in case 2, the denominator q of x is a product of linear factors, some of which are repeated. Okay, so suppose the linear factor ax plus b is repeated m times. So that would mean that the denominator q of x could have the expression ax plus b to the power m in the denominator. Well, in a case like this, the partial fraction decomposition accounts for each of the intermediate powers of ax plus b. So we're going to have, since they're linear factors, we're going to have m constants, a sub 1, a sub 2, up through a sub m. And the first partial fraction is a sub 1 over ax plus b. The next one is a sub 2 over ax plus b to the second, and so on. And the very last partial fraction, a sub m over ax plus b to the m. Okay, let's look at this example. We have the indefinite integral of a proper rational function. The degree of the numerator is 2, and the degree of the denominator is 3. If you were to multiply those factors, the leading term for q of x in the denominator is x to the third. So it is a proper rational function. And we see that the linear factor x plus 1 is repeated twice, x plus 1 to the second. Okay, so if we write the result by applying the partial fraction decomposition theorem, then 2x squared plus 3x plus 4 divided by x plus 1 squared times x minus 2 is a over x plus 1 to the first plus b over x plus 1 to the second plus c over the other linear factor x minus 2. Okay, I'm going to start off by multiplying every term on both sides by the least common denominator, like we did in the previous example. But then I'll use a different method for finding a, b, and c. Okay, so the least common denominator is just that denominator, x plus 1 squared times x minus 2. So when we multiply every term on both sides of this equation, on the left-hand side, the denominators all are canceled out. So the left-hand side becomes 2x squared plus 3x plus 4. And when we multiply the least common denominator by a over x plus 1, only one factor of x plus 1 cancels. So we still have a times x plus 1 times, oops. So a times x plus 1 times x minus 2. And then b over x plus 1 squared, the x plus 1 squareds cancel, so we get plus b times x minus 2. And then c over x minus 2 times the least common denominator, x minus 2 factors cancel. So we get plus c times x plus 1 squared. Okay, so I'm going to multiply all of those factors out on the right-hand side and combine like terms. And so it turns out that whenever a polynomial is equal to a polynomial, then the coefficients of corresponding terms must be equal. So that's the idea behind this method. We'll leave the left-hand side the way it is. And we'll do some multiplication. I'll multiply x plus 1 times x minus 2 first, and then afterwards multiply by a. So x plus 1 times x minus 2, we get x squared minus x minus 2. Then b times x minus 2 is just bx minus 2b. And then plus c times x plus 1 squared. When we square x plus 1, we get x squared plus 2x plus 1. Okay, so this method is also tedious. This is a fairly simple example. But let's multiply a times x squared minus x minus 2. We get ax squared minus ax minus 2b. We'll leave this term the way it is for now, plus bx minus 2b. And then multiply c times the trinomial x squared plus 2x plus 1. We get c times x squared plus 2cx plus 1. Whoops. Sorry, plus c. C times 1 is c. Dang. Okay, now on the right-hand side, let's identify the terms that have x squared. We have ax squared plus cx squared. Those are the only terms with x squared. So we'll write this as the quantity a plus b times x squared. Okay, so we've dealt with ax squared and cx squared. Now we'll identify the terms that have just x.
Professor, I have a question.
We have minus ax plus bx plus 2cx. Just to avoid confusion, instead of writing minus a first, I'm going to put plus, and then in parentheses, I'm going to write down at least one of the positive coefficients. So plus b, and then I'm going to write minus a plus 2c. This is times x. So we dealt with all of the terms that just have x.
Professor?
And then there's a constant. So the constant on the right-hand side is minus 2b. Did I do something wrong? Yeah, I did something wrong.
I think that's supposed to be 2a instead of 2.
This should not be minus 2b. This should be minus 2a. Okay, so the constant minus 2a minus 2b plus c. Just for convenience, I'm going to write it as plus c minus 2a minus 2b. Okay, so the coefficient 2, on the left-hand side, we have 2x squared. On the right-hand side, the coefficient of x squared is a plus b. So it has to be the case that a plus b is equal to 2. Then the coefficient of x on the left is 3. The coefficient of x on the right is b minus a plus 2c. So we write b minus a plus 2c equals 3. And then the constants must be equal. On the right-hand side, the constant is c minus 2a minus 2b. And this has to be equal to 4.
Hang on. Something doesn't look right. That a plus b times x squared, shouldn't that be a plus c times x squared?
Oh. Yeah. You're right. This should be a plus c. Yeah, so we have a plus c equals 2. So how many other mistakes did I make? So ax squared plus ax minus 2a plus bx minus 2b. I don't see any others. That doesn't mean there aren't any, but yeah, thanks for pointing that out. Okay, so a plus c is 2, b minus a plus 2c is 3, c minus 2a minus 2b is 4. Okay, well, the nice thing is we have 3 equations with 3 unknowns. The unknowns are a, b, and c. And if you have 3 independent equations with 3 unknowns, then there's a solution for all 3 unknowns. So I guess what we can do, we can begin with the simplest equation, and we can write a equals 2 minus c. And then in the other equations, replace a with 2 minus c. So be careful with the arithmetic. So if I subtract a, I'm going to subtract 2 and subtract negative c. So I get b minus 2 plus c plus 2c equals 3. Let's simplify this a little bit. So we get b, if I add 2 to both sides and add c plus 2c, I get b plus 3c equals 5. And then in this equation over here, we'll replace a with 2 minus c. So I get c minus 2 times 2. I'll write it in more detail. C minus 2 times quantity 2 minus c minus 2b equals 4. And we'll simplify this. We get c minus 4 plus 2c minus 2b equals 4. Okay, so I'm going to add 4 to both sides and add c to 2c. So I get 3c minus 2b equals 8. Okay, we're not in too bad of a spot here. let's focus on these two equations, b plus 3c equals 5, and 3c minus 2b equals 8. So I'm going to solve this for 3c by adding 2b to both sides. So I get 3c equals 2b plus 8. And then in the other equation, I'm going to replace 3c with 2b plus 8. So I'll get b plus 2b plus 8 equals 5. Subtract 8 and also combine b plus 2b. So I get 3b equals -3. And now we know that b is equal to -1. And since b is -1, we can find c now. So 3c, 2 times -1 is -2. -2 plus 8 is +6. Divide both sides by 3, we get c equals 2. So now we know that c is 2. So we're making progress. And then A is 2 minus c, but since c is 2, A is 0. Okay, it looks pretty messy, doesn't it? Okay, but let's go back up here to the original partial fraction decomposition. We found that A is 0, B is -1, and C is +2. So all we have to do is evaluate. I'll write it down here. The indefinite integral in terms of partial fractions becomes the indefinite integral of -1 over x plus 1 to the second plus 2 over x minus 2 dx. This is the result of the partial fraction decomposition. So we're about out of time. This is going to be, if you use U substitution, then this will turn out to be, since there's a negative, it will be 1 over x plus 1, and then plus 2 times the natural log of x minus 2 plus the constant. Okay, I think we're out of time. That's the first part of section 7.4. We'll discuss the next 2 cases tomorrow. But that's all for today.